Thank you, Florence. Thank you very much for the invitation. So I am here despite the traffic problems. So as Florence mentioned, I will talk about hybrid AI. I will explain in a moment what I mean with that. And I will show how we can make use of both knowledge and data for image understanding with examples in medical image analysis, image understanding. C'est aussi ça. Okay. So what we will mean here by image understanding is to go beyond just recognizing individual objects, but also assessing the whole structure of a scene by identifying objects, but also the way they are organized in space, in order to be able to provide a global description of the image and of the scene that is observed. And so we want to extract semantics from image, which is not directly in the image. And for that, we will show how we can make use of models and prior knowledge. And the final aim could be providing a linguistic description of the image. And then we have to think about what is a description, in which language do we have to provide this description. And for instance, if we are looking at this brain image here, c'est où le pointeur? Je sais pas. Bon, je sais pas. Here, we can just say, for instance, it's a magnetic resonance image of a brain with a pathology that we can see in this region. Or if medical doctor wants to explain to the patients what is going on, he has to go into more details, so the language will be different. And he will have to explain that the lesion is in that part of the brain, and that explains why the patient has problem seeing, reading, cognitive problems, etc., depending on the location of the tumor. And if the radiologist, for instance, is going to speak with other medical experts from different fields, then he has to provide even deeper explanations. So, for instance, explaining what is the mutation of the gene that is responsible of this tumor, etc. So, I'm not a medical expert, so I don't know what is in this image, but that's the idea. So, we have to think about the language. Alors, en fait, j'ai un écho dans le.
Il est dans l'ordinateur?
Ouais. Enfin, j'ai la voix qui revient de là. Enfin, bon, c'est pas très gênant, mais je parle au-dessus. Mais je m'entends. Le
pointeur, c'est le premier bouton là en haut.
C'est ça? Ouais, mais en fait, si je pointe là, ceux qui sont à distance, ils voient pas, donc la souris, c'est peut-être pas plus mal.
Il y a un écho qui sort de là.
Ouais. Je sais pas, peut-être quelqu'un qui n'a pas son micro coupé ou. Bon, c'est pas très grave. Hein,
je sais pas.
Okay. Okay, so I'm sorry, I'm not going to speak much about statistics, which was the aim of this day, but still there are a lot of information we can gather from data and from accumulated data. And the question is, can we find everything in the data? And indeed, there are a lot of methods which are very powerful with the development of deep learning methods, for instance, that make use of big data sets and that can extract information and knowledge and solve problems using that. But there are several problems. So sometimes the access to data is limited. And I'm working in particular with pediatric images where we have less images. And we may not have enough annotations on this data. And all this is very costly. And what I think is that in this domain, in particular in medical imaging, we have gathered a lot of knowledge over the centuries. And the idea is to make use of both the data and the knowledge we have. And we have also to deal with heterogeneity, but I won't speak much about that in this presentation. Alors, j'ai perdu le pointeur. Okay, so let's take the example of pediatric images. So the difficulty with respect to adult images, for instance, is that we have a lot of specificity. So the patients are different, of course, in morphology, size, etc., but also in the type of pathologies they have, and in the appearance of these pathologies in images. So images are very different, and for many reasons. And also the way we acquire images is much more constrained with children than with adults, and this induces also a lot of difference. And another problem is that we have not so many data, and that's good for the children. And we don't have much also control data, so that means example of children with nothing, for instance, because they are not going to have an examination if they have nothing. So it's very difficult to have control data and to know what is a control case, a normal case. Another problem we have is that, so in many domains there are a lot of databases that are stored and accessible to everyone. With pediatric imaging, it's much more difficult, and we have to find a good compromise between sharing the data and protecting the persons and their data. So that's an additional difficulty. And all this makes the usual problem of detection of a lesion of an organ, segmentation, recognition, etc., much more difficult tasks than on adult images. So what we can do still is to try to design methods and tools to provide pediatric radiologists or surgeons with useful methods to aid them for diagnosis, for surgery planning, treatment planning, follow-up of the patients, etc. And still we can do something. So just to show an example, we have here on the left pediatric images of the brain here and of the abdomen here. And for instance, here on the abdomen, we have here a big lesion, which is very different from what we have on adults. So, for instance, we can compare here adult images and children images. And of course, the size of the organ is much smaller on children than on adults. But since the type of tumors is completely different, here we have tumors that can be in comparison much larger than the ones on adults. And this makes usual methods based on transfer learning, for instance, very difficult to be instantiated on this image. So we have to add something to take the specificities into account. So now I'm coming to hybrid artificial intelligence. So what I mean by this is not just combining deep learning with symbolic methods, but in a more general sense, combining different fields of artificial intelligence. So this can be different methods for knowledge representation and reasoning based on logics, for instance, and methods coming from data, methods to represent uncertainty or imprecision, methods to represent the structure of a scene, for instance, based on graphs, etc. And the main question is how to find the good balance between what we can do with data and what we can do with knowledge representation and reasoning on a more symbolic way. And we can, though it's very rough, of course, but looking at the studies in cognitive science, in particular Kahneman's study, which differentiated between two systems of reasoning. And very roughly, again, we can approximate the system one of Kahneman's as methods just relying on data and trying to find correlations and infer things very rapidly. And system two of Kahneman's that relies on more knowledge we have that has been gathered and that calls for some reasoning, which takes more time and which is less immediate. So that's a parallel we could do. And what I think is that using these hybrid methods will allow to have stronger links between knowledge and data, and between a result, a prediction, for instance, and data, which can be explained. So that's the final aim, to have something that is also explainable. And so, of course, we have to solve the semantic gap problem. So if we have knowledge expressed in a symbolic way, we have to convert it in someone that is useful with respect to the image, with the numerical data we have in the image. So, for instance, if we say that an organ is big, for instance, what does it mean to be big? And it's clearly not the same if we are speaking of medical images, or if we are speaking of cells in biological images, or if we are speaking of planets in astrophysics, for instance, or whatever. So the concept big can be easy to understand, but what it means particularly in a specific field of applications needs to be modeled in some way. Okay, and another directions we expect is that using both knowledge and data could be a mean to compensate for biases in all these methods. So that's an open questions, and also questions related to ethics. It's an open question. So now about explainability. So this is not a new field at all. And so this is a very old question, so starting from antiquity, but of course without any formal models of explainability. And then this was formalized more mathematically at the end of the 19th century, so it's not new. And in particular, we can mention the work by Peirce, who modeled abductive reasoning. That means trying to find explanations from observations based on a knowledge base, for instance, using a logical formalism. So a mathematical modeling of what is abduction and what is explanatory reasoning. So it's not new. So now we speak a lot about explainability for networks, but it's not at all a new thing. And we can also distinguish between different things. So for instance, what is interpretability and what is explainability. So there are works trying to differentiate between these. And for instance, we can mention the work by Christophe Denis and Frank Varenne, who distinguished interpretability as having elements that compose a system that are meaningful for a human. And explainability has a causal chain among all these elements. So it's really related to causality. So not just explaining different elements and not just finding correlations. So that's very important. And we have been working in that direction in several domains. So for instance, from a purely logical point of view, but also for image understanding using spatial reasoning methods. And so I will just mention one work that I did with several colleagues, and including at Centrale Supélec, very close to here. And what we did is to, in some logic, so to formalize knowledge in that logic, we have some observations that can be also formalized using logical formulas, for instance. And then we are trying to find explanations based on that. And the mathematical framework is the one of lattice, so in particular complete lattice. So it's an algebraic framework in which we can model a lot of different logics, and also operators, for instance, coming from the field of mathematical morphology. And our idea was to try to stratify the models of a formula using dilations and erosions, and then, for instance, and use that to solve several problems. So, for instance, for abductive reasoning, we are going to find the models of a formula that are the most central in the formula using successive erosions, but still being consistent with the observation that we are trying to explain. So we have this amounts to add formulas to the theory, which will be the explanation, and that makes the theory consistent with the explainable formula while being more central, which means also more robustness. So that's illustrated here. So we have here the background knowledge or the theory, the observation that could be explained, so it's represented here as a set of models, for instance, and we are going to perform successive erosion of sigma here, and until we stay consistent with the observation. And the explanation can be found in these regions here, in this set of models. So the same idea can be applied for different types of reasoning. So for instance, revision, fusion or belief mergings, etc. But I'm not going into details here. And thanks to this strong algebraic framework, this applies to propositional logics, but also to many different other logics, in particular model logics that could be useful for spatial reasoning, and many others. So, but now the question is that here it's purely symbolic. So how can we make the links with quantitative information, with images, etc. So again, the idea of hybrid intelligence, artificial intelligence, is to merge different fields of AI. And what I'm making use is of a lot of different theories. So, for instance, abstract logics, as I mentioned before. So this will be useful to represent knowledge and reasoning on that. Then if we are interested in assessing the structure of a scene, see how objects in a scene are arranged in space in order to have a more global understanding of the image, we can make use of structural representations, such as graphs or hypergraphs. And this can apply both to the images. So for instance, where we can have a graph representing spatial relations between different regions in the image, or at structural level, where we can make use of conceptual graphs or ontologies to represent knowledge in a structured way. So it applies to both. In all these representations, we have a lot of imprecision. So either related to the data or in the way we represent knowledge to link it with data. So, for instance, if I take the example of big before, what does it mean big? So it's something that is intrinsically imprecise and depends on the context, and then we can make use of fuzzy sets in order to represent this imprecision. And this will allow us to link a concept with information extracted from the image. And a useful tool in fuzzy sets for that is the one of linguistic variables that makes the links between completely abstract representation and concrete representation in some domain, for instance, the image space, and solve the semantic gap issue in that way. And of course, we can also use machine learning methods that exploit data sets, etc. Okay, so that's just a schematic representation of what I'm just saying. And in all my work, a constant is a strong algebraic frameworks using lattices that is useful for many types of representation, because so logics, formulas in logics, fuzzy sets, graphs, etc. We can all have, for all these formalisms, we can have a lattice structure on them, and that makes things coherent and unified in some way. So now let's detail a little bit more this idea of using structural information to have global interpretation of an image. And a large part of my work was dedicated to spatial relations. And again, with this algebraic framework, it's interesting to notice that several spatial relations can be conveniently represented using mathematical morphology. And then, so for instance, we can define set theoretical relations or topological relations, distances, etc., using mostly dilations and erosion, so very simple tools from mathematical morphology. And again, the advantage of this is that we can apply this to a lot of different representation of the spatial information, whether a set, a fuzzy set to cope with the imprecision on the objects, or with purely abstract representation. And it will be the very same formalism to define these spatial relations. So that's, again, an advantage of relying on these algebraic structures. Let's give an example. So let's imagine that we have at an abstract level a concept, so described by a linguistic value of some variable. So for instance, if we are interested in size or distance, we can say it's large, medium, etc. So we have a set of possible linguistic values. And now to define the meaning of these values, we have to go to the concrete domain, for instance, to the image space. And this can be done using these tools of linguistic values in the fuzzy sets theory. So for instance, if we have some knowledge that an object is at medium distance of another one, we can represent what does it mean to be medium here as a fuzzy set on a set of distance. And then we can convert this as dilations in the image space. Similarly, if we are interested in modeling what does it mean to be to the right of an object, so we have to define what is the meaning of right, which is intrinsically imprecise. So for instance, if I say that this object for you is to the right of the computer, so you will say, okay, it's to the right. And then if I am moving like this, you will say, okay, it's to the right, but maybe to a less extent. And at some point, you will say, no, it's not to the right. And this can be modeled very easily using fuzzy sets. And we can define the semantics of this relation as a fuzzy set in the spatial domain, in the image domain, basically. And here we have a fuzzy set representing to the right of, with high gray levels representing high degree of satisfactions of the relation. And this degree decreases when we go apart of the main direction. And this can be tuned, of course, according to the application or even learned on sets of data. And then if we have an object and we want to know what is the region to the right of this object, we just have to dilate the object by this fuzzy sets considered as a structuring element in mathematical morphology. So that's illustrated here. We have this square here, which is in red in this image. Here, the structuring element representing the semantics of right and the result of the dilation of this object. Mm-hmm. So there are many relations that we can model in this way, and from that we can infer different things. So, for instance, we can consider this as a region of interest, where we can find another object satisfying this relation to be to the right of the square. Or if we know another object like object B here, we can look where it is in this kind of map, and then compute the degree of membership or satisfaction degree of the relation, and aggregate over all the values of the point of B to decide to which degree B is to the right of the square. These spatial relations are very useful to describe, again, the organization of objects in a scene, and that's an information that is very often present in the description of the knowledge we have. In particular in medical imaging, so we have knowledge, for instance, that an organ is to the right or below another one, and that's usual descriptions we can find in medical textbooks, for instance. And this okay. So we have used this quite intensively to recognize objects in images based on information we have on spatial relations. Here is an example where we have CT images of the lungs, and we want to look at the heart region, which is here. So these are 3D images, but here we have just two orthogonal slices, an axial slice and a frontal slice. And it is very difficult to detect the heart directly in such images because of the lack of contrast. So the gray level is very similar to the one of the liver, which is here, or of the aorta that we can see here. But it's obvious on this image that lungs, so the black parts, are much easier to detect. So even if someone has never seen an image or an image processing method, they can imagine that lungs are much easier to detect because they are very dark with respect to the other structures. And now we can start by detecting the lungs and then make use of the knowledge we have about the position of the heart with respect to the lungs. So for instance, we can describe the heart as being between the lungs, somewhat closer to the left lungs than to the right one. We have also a position with respect to the anterior and posterior part of the body, etc. So we can model all these relations, as I mentioned before, for the relation to the right of, combine all this to restrict strongly the search region, so the region of interest where we can find the heart, and then we can indeed find the region of the heart. And now, how can this help for explainability? So in the other way around, we can say, so well, we have found this region, which is a part of the knowledge that was actually involved in the result. So how can we link the result we have with the knowledge that was actually used in a meaningful way? And then we can say that this region is the heart because it is between the lungs, for instance, because this relation has been intensively involved in the recognition. So it goes two ways. So from the knowledge to the data, and conversely, looking at which knowledge was helpful to make the decision, go back to the interpretation and explainability of the reasoning that was done. So that's in the second point. So here are a few examples that have been done with many other people that are mentioned here, so I won't have time to thank all of them individually, but their names are here. And we use this idea to segment and recognize at the same time different structures in the brain, including pathologies, with different approaches. For instance, we can model the knowledge we have as a graph, extract some homogeneous regions from images, build a graph from that, and then try to find a morphism between the two graphs. But that's quite complicated because we cannot expect to have an isomorphism. So we have to optimize an objective function, which is not that easy to derive. And we have also developed two other methods that work very well. One is to use the previous idea of defining a region of interest to find structures in a sequential way. So that means that we start from a structure which is quite easy to detect. Then we try to find another one based on the relationship to that initial structures. And then we move on like this from structure to the structure. So that means that we can start with the easiest one, and at the end of the sequence, we have structures that are maybe more difficult to detect, but we have gathered so many information from the image that it becomes easier. And another method we developed was to express the problem as a constraint satisfaction problem, and then iterate over all structures simultaneously by trying to reduce the potential regions for each structure, again by making use of these spatial relations. So the idea is to transpose every spatial relations into a constraint and a propagation in a constraint satisfaction problem. So here we have some results on a few brain images with pathologies, and the advantage of using spatial relations more than shape and size is that even in case of strong deformations due to tumors, for instance, it works very well because the spatial relations are more robust to this type of pathologies than intrinsic properties of the objects. And here is another example where we use the same ideas to detect fasciculus in the brain, so sets of white matter fibers that links several regions in the brain, again based on the description of the path that these bundles follow in the brain. So we have here two extracted here in the brain. So now once we have this, we can use this to try to find explanations. So again, applying the abductive reasoning I mentioned at the beginning. And now we have the knowledge expressed in some logics, the observations that are the images, and also the result of this initial detection and recognition of object, and then we can infer a higher level description of the whole sense. So for instance, here we could describe this as an image with a tumor which is non-enhanced and has a small deformation effect of the other object. So all this can be inferred from the knowledge we have and from the description, the result of the segmentation and result of recognition. We can also use this for type of results to plan a surgery, for instance, to help planning a surgery, or for treatment follow-up, etc. So I will show an example for surgery, where so we have big projects with Necker Hospital on pediatric patients, of course. And here the questions was how to plan a surgery in the pelvis without having impact on the main nerves, which is of course very important for the children. So what we did is to make use of anatomical images and also from diffusion tensor imaging in magnetic resonance imaging, which provides information on these fibers. And then from all the fibers that can be extracted using any tractography algorithm, we try to identify the main nerves based again on their anatomical descriptions and the path these nerves follow with respect to the anatomical structures. And here is the results that merge several methods, so we cannot see the nerves here on this representation, but here it's again the application on the abdomen I've shown at the very beginning. So we have CT images of the abdomen, and from this we can extract a lot of different information. So for instance, the main organs, the lesions, also the blood vessels and the nerves, as mentioned before. And what were used to provide these 3D models of the patient, so it's a kind of digital twin of the patients based on the images, the own images of the patient. It merges methods using deep learning for the segmentation of the main organs, deep learning plus geometric model for the vessels, so described as elongated structures, and a more symbolic approach and spatial reasoning for the nerves, making use of the description of the path of the nerves, as I mentioned before. And so I like this example very much because it's an example where the surgeon changed the decision of surgery based on these 3D models. So looking at the image, the impression that there were a lot of tumors, and indeed there were a lot of tumors, and that it would not possible to save the organs. And after seeing the 3D models, the surgeon could get a better understanding of the relations between the lesions part and the normal parts of the organs, here the kidneys, and she decided to try to keep at least a part of the kidneys. And of course, the consequence for the child was completely different, with living without kidneys, so you can imagine what it means, and keeping a part of the kidney, which means that they will continue to work to some extent. So it changed completely, and it worked. So we are very proud of this example. And also this type of models is a way to interact with the patients, and in that case with the parents of the children, which are of course very anxious. And when they see these 3D models, they understand better what is going on, what are the possible consequences of the surgery, and they are more ready to accept it. So it's also a way to help for explaining, to having this 3D model. So again, a way of finding explanations in some way. And here is an example where the objective was to detect the tears in the meniscus here, in this region. And using a deep learning method, so it used an ensemble method, but that's not very important. So the detection was pretty good, so the results were good. But looking at interpretation maps, so just using GradCam, for instance, or things like this, we could observe that the regions that contribute the most, so the red ones, are completely outside of the region of interest. So when showing this to the radiologists, they were not happy at all with the results. And they said, so I cannot be confident if I see something like this. And so what we did is to combine the original image with some image transformed using some, again, morphological method in order to highlight the region of interest based on their shape, appearance. So again, using the knowledge we have about these tiers in this data. So now the input is these two images, the original one and the transformed one based on the knowledge we have. And then the results were slightly improved, but that's not so important. And the interpretation map was much more convincing. And so the results were better accepted by the radiologist. Another example was to use just transfer learning from adults to children, so which is a way to solve the problem. So here it's mostly deep learning methods, so there is no more not much symbolic here. And so I think I have to be a little bit faster. So I will just show here the results. So the idea was to train a network on adults and then transfer it on very few children images. And it worked very well. So we can see here example of detecting the corpus callosum on children, so which are this structure here, which is very important in particular on newborns children to assess what are the risk of problem in the development of cognitive functions. And it works on different types of images, different types of machines, etc. So it's quite robust to the type of acquisition. And from that, we can derive these curves, which shows that at different positions here along the corpus callosum, so we look at different segments here along the structure, and we compute the thickness of the corpus callosum at all these locations, and compare from date to date how this thickness evolves. And we could have directly provided this, and then we can see that in that region of the corpus callosum, which is somewhere here, there is a big change in thickness. But again, in order to make the result acceptable for the medical experts, we have to provide an explanation of why is this thickness. And here the explanation can be simply the segmentation. So we cannot skip this step of segmentation because it's a reference to the image and the way the medical expert can interpret the results on these curves. So this is the quantitative result the expert expect, but they have to rely on the segmentation to be confident in the results. So again, this raises the question of which level of interpretability, of explainability we need. So just to conclude, a few words about the work we are going to do now. So we are relying on the work by Tim Miller, which defined what should be an explanation based on a lot of a summary of a lot of studies in philosophy, in cognitive sciences, etc., in sociology also. And we worked mostly on the idea of finding causes rather than just correlations. And we are doing so using different types of methods, using argumentation framework, so abstract argumentation framework, establish their links with causal models, so relying on the work of Alpern and Peer, for instance. And we are also making the link with action languages, which allows involving time in the way arguments are proposed, for instance, which is an important thing. And we are also working on this idea of having contrastive explanation. That means if, for instance, if a radiologist expects that what he will find in the image is A, but an algorithm says B, then we have to find an explanation of the type, so why B rather than A that was expected. And by discussing with radiologists, it happens that they need explanation in case the result is not what they have expected. So this idea of contrast is very important to find explanations, and we are working with that in the framework of causal models, but with a layer of fuzzy sets in order to represent the imprecision we may have in the data, in the decision, etc. Okay, so that's the next step, basically, which are also summarized here. So I think I've been long enough, so I have to stop here. Sorry for the time.
Thanks a lot, Isabelle. I'm sorry for the situation. I think you probably have a strong headache because of the echo, but I don't know, we have to fix it for the next talk, I think. Any questions? Yes.
How long does it take, in fact, to build a digital twin from the images and then to be able to model in a functional way the position of the organs and so on, and then to combine everything and then to...
So it depends what we mean by how long it takes. It took years to design the methods, the models, etc. But now what we have is for instance, all the parts that is based on deep learning, it takes time to train, but once it's trained in inference, it's very fast. And then we may need some manual corrections, for instance, in some cases, but they are reduced to a few minutes with respect to several hours if we find everything by hand. So at inference, it's very, very fast. And for the logical reasoning part, it's very fast also because it's just checking a few results. So the computation of the relations is not, it's not very heavy. It's a linear complexity in the number of voxels in the image. So it's not, it doesn't take long, it's just a few minutes.
It's the time of execution. I was thinking, for example, I am an industrial partner, and I have pictures with some objects and some relation, like, for example, a motor for a car. I don't know. And I want to be able to build, in fact, such a stream from the images and then to the decision process using a digital twin. From your point of view and your experience, how long does it take? It's 1 year, 5 years to be able to...
I don't know anything about motors, but... So it depends. If the expert knowledge is pretty well clear what should be used, etc., it can be very fast. But for instance, with in the medical field, it took a very long time to understand what is really useful, what is not, and so there was really a dialogue to be established. And but in 1 year you can have results for sure. But yeah.
Yes, it was about when you have detected some tumors in your like good example where you are proud of. How do you do to detect abnormality if you have expert knowledge of what it should be as usual?
So here we do not rely on, for instance, a normal shape of kidney, for instance. So we exploit mostly the information contained in the image to find out that there are indeed tumors to be detected. Is that what you mean? Or?
Yes, because you were speaking about relation, about it is at the right of this thing.
Yes, that's for the normal organs.
Okay, but when you want to detect tumors, you don't use that stuff?
No, because in that case, no, because they can be everywhere. So we don't have any prior knowledge about where are the tumors, how they are related to the organs, etc. And that's assessed a posteriori on the result, but not used a priori.
Okay. So you don't distinguish the kidney from the tumors automatically?
Yes, we do. We do, but using a learning approach without modeling explicitly where the tumors are.
Okay, so this is a part of your method which is not very explainable.
It can be explainable a posteriori. So based on by comparing, for instance, the models with the image, and then try to describe the location of the tumor, but it's done on the results, so not a priori. We can,
So maybe to follow up questions. So out of the examples you presented, which one are indeed explanation a posteriori, and which one are actually use the knowledge for taking the
for this example? It depends on the application, but in these particular applications, we use mostly learning from data for the organs and the kidneys and the lesion. For the vessel tree, we used both learning from data and prior information on what is a vessel, so an elongated structure. So we compute parameters called vesselness in order to force the network to focus on this. So it's really a mix of both. And for the nerves, it's more symbolic spatial reasoning.
Maybe I have a question related to this one. I understand that injecting knowledge when you have very few data is very useful, but is there any framework that you can use that can say, okay, but the knowledge was not adapted or was not sufficient, or was is there more adapted frameworks to take into account the fact that the prior knowledge that you are trying to introduce, for instance, in the learning stage, could be unreliable?
Yes, that's done in the way we model this knowledge. We model it in an imprecise way, which should be robust to change from one patient to another one, to deformations, etc. So that's the interest of fuzzy modeling, because it accounts for all this possible variability and imprecision. And so. But there are probably many other methods to do so.
About ethical aspects, you were speaking a little bit about the bias at the beginning of the presentation, the way to use all these techniques to counterbalance bias. How?
Yeah, that's still open questions, but there are start to be work on that. For instance, trying what a network is really using, since it learns patterns. If there is some patterns in the data that comes from some bias, we could try to identify it. So, for instance, a colleague of mine, Pietro Gori, is working on that to try to infer, for instance, whether the age of the patient is implicitly used by the network. Concerning spatial relations, we worked also to know whether the networks implicitly use spatial relations or not, and things like that. So that's an aspect.
Okay, thanks again.